Hello, in this video we are going to learn some very fundamental physics. Einstein, Podolsky and Rosen, they tried to prove in their paper titled "Can the quantum mechanical description of reality be considered complete?" This was the title of their paper. So they were asking if the quantum mechanics is actually complete, because the earlier interpretation of the quantum mechanics, known as the Copenhagen interpretation, seemed to be absurd to a lot of researchers. The people who found Copenhagen interpretation to be absurd and questioned about the completeness of the quantum mechanical interpretation were called as realists. So by definition, Einstein, Podolsky and Rosen were realists. Now what is realism? We will look into it. So they thought that the properties of physical systems have a definite value, or what we can call as objective reality, whether you observe the system or not. That is, even before measurement, the system is in a definite state. If you think of the Schrodinger's cat's thought experiment, in that the cat was either dead or alive already, that is before the measurement or before opening the box. So this is nothing but the classical view of looking at things. Another way to say this is that a given property of a system has a defined value before a measurement is made. They argued in their paper that the conventional view of quantum mechanics, the Copenhagen interpretation, which is a non-realist theory, is in those times violates the special theory of relativity, or the principle of locality. The people who believe in interpretations like Copenhagen are called as orthodox. Hence, the interpretation should be wrong. That is what their argument was. Hence, any interpretation of quantum mechanics should contain realism. That is what Einstein, Podolsky and Rosen tried to propose in their paper. What is the principle of locality? It says that measurement, let's look at only in the quantum mechanical sense, or what we are interested in quantum mechanics. Measurement of particle A in no way affects state of a spatially separated particle B. The principle of realism says that this is constrained by the principle of the special relativity principle, that nothing can travel faster than light. The other is realism, that is the values of the measurable properties, of each particle are objectively real. They have definite values prior to the measurement, and regardless of whether or not they are observed or measured. In 1957, David Bohm presented a simpler version of the one presented by EPR, arguing against the completeness of the Copenhagen interpretation of quantum mechanics. So let us uh, let us do an experiment where there is a photon source and it emits light in both directions. Let's say on one end there is Alice and on the other there is Bob doing some measurement on these photons with certain polarization state. Let us say that the measurements are done in the 0 and 1 basis, the computational basis, that is the eigenvectors of the operator or the observable sigma z. Let us say that these are the results that they find. Whenever Alice finds 0, Bob finds 1, Bob finds 1, Alice finds 0, Alice finds 1, Bob finds 0, 0, 1, and it goes on. So they sample the measurements, Alice and Bob, and then they compare with each other. What they find is 50% of time it is Alice finding 0 and Bob finding 1, and the other 50% of time it is Alice finding 1 and Bob finding 0. So there are two ways to explain this, either using the quantum mechanics or using the classical mechanics. In the classical mechanics way, we can think that this photon source already was sending out particles or photons in a definite polarization state, and it was already, there was some mechanism that it chose that whenever it sends out 0 on to Alice, it sends out 1 to Bob and vice versa. So there is a classical way to think of this, and it can so happen. There is a quantum mechanical explanation to this also. The classical way is what EPR and David Bohm were arguing for, and it is backing up the theory of local realism. That is, any theory has to be a local realist theory. Any theory explaining the such kind of physics has to be a local realist theory. So the quantum, now getting back to what I was saying about quantum mechanics, it can be explained also with quantum mechanics. So now how do we know which one is right and which one is wrong? So to explain that, John Bell came up with an idea, and it is called as the Bell's theorem. In 1964, these ideas were taken much further by the brilliant theoretical physicist John S. Bell. By considering polarization measurements along three non-orthogonal directions, which we can label as A bar, B bar and C bar. They are three non-orthogonal directions. Let's name as A bar, B bar and C bar. So the measurements are performed along three non-orthogonal directions of the polarizations of the photons. And he said that we can derive an inequality if the local realist theories are correct. For local realist theories like that of EPR and Bohm. Now, if this inequality gets violated, then the Copenhagen interpretation or the orthodox interpretations are correct. Orthodox interpretations are correct if the inequality gets violated. This inequality is experimentally testable, and all experiments show that it is violated, hence forcing us to discard either locality or realism. Now again, as locality is experimentally backed, realism needs to be discarded. So this was the whole argument of Bell's theorem and later experimental tests. So to explain classical logic, we will be using classical logic in this and compare and derive the Bell's inequality. So let us look at a very simple example. Let us say that there are people wearing hats, scarves and gloves. Let's say some of them are not wearing hats, some are not wearing scarf, some are not wearing gloves, and so on. So we can create a Venn diagram of the people as such. So let's say these are the people who wear gloves, these are the people who wear scarf, and these are the people who wear hat. Let's name them as A, B and C. Let us say that the people who are only wearing gloves and nothing else are denoted by Q, that is be this cross section. This is R, this is S, T, U, V, W. So we have named it as such. That is, let's say Q is the set of all people wearing gloves but no hats and scarf. R are the people who wear gloves and scarf but no hat, and so on. So what we can see over here is the set Q, the subset Q plus R plus T plus S has to be greater than or equal to Q plus R, because as the set is positive, or we can say at 0 or positive, so this becomes Q plus R plus T plus S is greater than or equal to Q plus R, as this can't be negative, T and S, or neither can Q and R be. So Q plus T plus R plus S is greater than Q plus R. So we just simply rearranged the positions. Now let's say there are N1 people over here, N2 people, N3 and N4, and we say that N are the total number of then it can be easily derived that probability of being in the set A and not in B, that is what it is, right? Q plus T is being in the set A but not in B. It can be in the set C also. So probability of a person being in the set B and not C is greater than probability of it being in someone being in A and not in C. So this is a very simple argument and it can be derived easily. This is nothing but Bell's inequality. So we should understand that before taking the data of the people, they were already in the definite state, wearing hats, gloves and scarf. So we are considering a classical theory over here, that is a local realist theory, which was what the argument, which was what EPR and Bohm were considering. So this kind of inequality should apply to all local realist theories. Now let us look at it for a physical system like that of photons, and then see what answer we get. Is the Bell inequality violated or not when we consider photons? Let us see. So let us replace the hats, gloves and scarf by measurements of the photon polarization in non-orthogonal directions. Replace hats, gloves and scarves by measurements of photon polarization, along three non-orthogonal directions, A bar, B bar and C bar. Let's say A bar is equal to 0 degree, B bar is equal to 22.5 degree and C bar is equal to 67.5 degree. So basically we will be doing measurements using such polarizers. A 0 degree A bar, 22.5 degree B bar and 67.5 degree C bar. So these analyzers we will be using. Let us say that there is a photon source as usual which is sending out photons in both directions, and then we do measurements on both sides such that we do measurements on both sides with different orientations, and we sample the results. So we can place, let's say, A bar over here, B bar over here, or A bar over here, A bar over here, and so on, and we can keep on repeating and randomly change the directions of the analyzers. And for different photons we keep on measuring whatever the result is get and sample our results. So basically whenever a photon approaches any analyzer, it either passes through it or it doesn't pass through it. That is what is the observation. A photon either passes through polarizer or it doesn't pass. So these are only the two possible outcomes. Let's say when it passes through polarizer, we denote that by plus. Does not pass through polarizer, we denote that event by minus. So if we tabulate the findings of, and we do this experiment n times, If we tabulate, then we see that the population goes as such: n1, n2, n3, n4, n5, n6, n7, n8, and Alice, let's say Alice is on one side and Bob on the other, and this is Bob's. So let's say there are n1 photons which are found to be, first of all let me just write the table. Yeah, so these are the findings that we will get, such that the n1 photons are as such, that is it they on the Alice's side, the photon will pass through A bar, B bar and C bar also, and on Bob's side the photon will not pass through A bar, B bar and C bar, and these are the division of the population of the pair of photons as such. n1 photons are in this manner, n2 photons are in this manner, n3 photons are in this manner, and 4 and so on. These are the all the exhaustive possibilities that we can have. Moreover, these n1, n2, n3 up to n8 will be equal to n, and all these ni's are obviously greater than or equal to 0, and hence even n is greater than or equal to 0. Let us say that whenever we do experiment, the Alice and Bob's does experiment, they choose opposite directions. They never choose the same direction for measurement. So there will be 6 possibilities, Alice and Bob. So if let's say Alice chooses A bar, Bob chooses B bar. Alice chooses A bar, Bob chooses C bar. Alice chooses B bar, Bob A bar, B bar, C bar, C bar, A bar and B bar. So these are the 6 possibilities when Alice and Bob decide to measure along opposite directions only. So the probability that Alice measures +1, probability that Alice measures +1 on her side and Bob measures +1 on his side for B bar is equal to n3 plus n4 divided by n. So on the left hand side, what we mean is that the probability that Alice takes the analyzer A bar and finds that the photon passes through, and Bob takes the analyzer B bar and also finds that the photon passes through. So the number of events in such a case are n3 plus n4, and dividing by the total number of events, we see that the probability is equal to n3 plus n4 divided by n. Let us check. If we check n3 and n4, Alice finds A bar equal to plus, Bob finds plus, Alice finds plus, Bob finds plus. That is what we needed. All other different populations can't give us such events. Then similarly, the probability that Alice sees that a photon passes when she uses A bar analyzer, and Bob finds the photon passes through when he uses the C bar analyzer, is equal to n2 plus n4 divided by n. Now similarly, the probability that Alice uses a C bar analyzer and finds that the photon passes, and simultaneously Bob uses a B bar analyzer and sees that the photon passes, is equal to n3 plus n7 divided by n. So we see as n3 plus n4 is always less than or equal to n3 plus n4 plus n2 plus n7. This is because all n are greater, so we just basically add more n over here, so it has to be obviously greater than that. But this can be always manipulated, and we can write this as n2 plus n4 plus n3 plus n7. So we just rearranged the terms, and if we divide this by n, we see that n3 plus n4 divided by n is less than or equal to n2 plus n4 divided by n plus n3 plus n7 divided by n. This is nothing but the probability that Alice uses an A bar analyzer and sees that the photon passes, and Bob uses the B bar analyzer and sees that the photon passes. So this has to be less than or equal to probability A bar equal to plus C bar equal to plus probability C bar is equal to plus and B bar is equal to plus. These are derived from these equations that we've derived earlier. So this is nothing but Bell's inequality that we saw earlier. If we see earlier, we assumed that states of the polarization of the photon were definite even before the measurement. What if we use a quantum mechanical theory? If we consider that the photons can be in superposition of states before the measurement, then QM argument, let's say, then any linearly polarized photon, let's denote it by psi theta, can be given as cos of theta 0 plus sine of theta 1. We can say that 0 is related to horizontal polarization and 1 is related to the vertical polarization states, such that 0 is less than or equal to theta is less than or equal to 180 degree. The probability that such a photon will pass through, let's say, an analyzer oriented at 0 degree, the probability that it will pass through the 0 degree is nothing but 0 psi mod square. So this is what? Nothing but cos square theta. And the probability that such a linearly polarized photon, as given by psi, doesn't pass through this 0 degree polarizer is 1 minus cos square theta, which is equal to sine square theta. So this is the probability that it will not pass through. If we see that, then it is equal to the probability of the state orthogonal to 0 state, that is the one which completely passes through the 0 degree polarizer, no matter what. So the states which are orthogonal to the direction of the to the angle of the polarizer, they have 100% do not pass through such a polarizer. So any state orthogonal to psi of theta in general can be given as psi of theta plus pi by 2. So this will be, if replacing the value of theta by theta plus pi by 2, it becomes equal to cos theta minus sin theta 1. So these are orthogonal to psi of theta and do not pass through at all against a polarizer, or you can call it as an analyzer oriented at theta degrees. We should also realize that, let's say we take the inner product psi of theta 1 and psi of theta 2, then this is equal to cos of theta 1 0 plus sin of theta 1 1 and cos of theta 2 0 plus sin of theta 2 1. If we expand this, we find that this is equal to cos of theta 1 cos of theta 2 plus sin of theta 1 sin of theta 2. Also, if we take such a inner product 0 with sin of theta 2 minus theta 1, we will find that this is equal to such a decomposition, and the final value is also equal to cos of theta 1 cos of theta 2 plus sin of theta 1 sin of theta 2. So we can say that psi of theta 1 psi of theta 2 is equal to 0 times psi of theta 2 minus theta 1. We will need this for later calculations. Let us say the photon source emits out states which are given as such: 1 by root 2 psi of theta psi of theta. So this is what the Alice gets and this is what Bob gets, plus psi of theta plus pi by 2 comma psi of theta plus pi by 2. So let's say that this is the state in which the photon source continuously emits on both sides. The combined state looks like this, and this is possible in quantum mechanics to write such a state, as we already saw in the previous video. Then let's say we do a measurement as such with these projection operators psi of theta psi of theta. So basically Alice measures in this direction, let's say 0 degree, and Bob measures in theta degrees. Or what we can say that Alice measures with a horizontal polarization and polarizer, and Bob measures with a polarizer at angle phi. Okay, let's denote this as phi. So the probability that let us say that Alice measures at phi 1 with the polarizer oriented as such, and Bob with polarizer oriented as such. Phi 1 degree and phi 2 degree. Then the probability that we find measurement as such is equal to psi phi 1 psi phi 2 acting on psi es. It gives out psi es. This is the combined state of the two photons being emitted. Mod square. So this is equal to 1 by root 2 psi phi 1 psi of theta psi phi 2 psi of theta plus psi phi 1 psi of theta plus pi by 2 times psi of phi 2 psi of theta plus pi by 2 mod square, and this is acting on the whole. So as we saw that psi of phi psi of theta is equal to 0 acting on psi of theta minus phi, this is equal to 0 acting on cos of theta minus phi, 0 plus sine of theta minus phi 1. So this turns out to be nothing but cos of theta minus phi. So these inner products, with these inner products we should get this to be equal to 1 by root 2 cos of theta minus phi 1 cos of theta minus phi 2 plus sine of theta minus phi 1 sine of theta minus phi 2 mod square. This is 1 by root 2 cos of half times cos of theta minus phi 1 minus theta plus phi 2 square. So this is half times cos square phi 2 minus phi 1. So this is the measurement probability of Alice getting psi phi 1 upon measurement and Bob getting psi phi 2 upon measurement using the polarizers as given in the diagram. So the probability that Alice tries to measure if the photon is oriented at 0 degrees and Bob tries to measure if it is oriented at 22.5 degree, this is nothing but A bar equal to plus and B bar is equal to plus. We saw in the experiment when we created the setup that we chose these particular angles for our polarizers. A bar equal to 0, B bar equal to 25 degree and C bar is equal to 67.5 degrees. So the probability that 0 degree comma 22.5 degrees as such over here, let us denote it properly. psi 0 degree psi 2 is nothing but the photon will pass through analyzer oriented at angle A bar for Alice, and the photon will pass through oriented at angle B bar for Bob, as B bar is equal to 22.5 degrees. So just replacing the values, it turns out this is half of cos square 22.5 minus 0 degrees. So it is half of cos square 22.5 degree, which approximately is 0.42. So this is nothing but the probability that Alice keeps an analyzer oriented at 0 degree and Bob keeps an 22.5 degree Celsius, 22.5 degree, and a photon passes through each of their polarizers. Similarly, probability as such will give us a value approximately equal to 0.07, and as such will give us a value approximately equal to 0.25. So these are nothing but the probabilities that Alice keeps a polarizer at an angle A bar and the photon passes through for her, and Bob keeps the polarizer at an angle C bar and the photon passes through his side, and this is as such. But we can see over here that 0.42 is greater than 0.07 plus 0.25. But we should have A bar equal to plus comma B bar equal to plus to be less than probability of A bar equal to plus comma C bar equal to plus probability C bar equal to plus B bar equal to plus. This is what Bell's inequality is. But it gets violated over here. So it seems that the quantum mechanical calculations can show that Bell's inequality gets violated. So using Bell's inequality, we can distinguish if local realism is a correct or not. It turns out that Bell's inequality gets violated in experiments. So we need either use to discard locality principle or the realism principle. But it turns out that locality is also experimentally backed by special relativity. Hence, we need to discard the idea of realism, that is, the states of the photon polarization are definite before the measurement is performed. So after a very long derivation of the Bell's inequality, I think we should ponder upon these such problems. Thank you.